Today, we'll specifically be looking at the anatomy and biology of the rectus femoris muscle. The rectus femoris is part of the quadriceps group. It is the only muscle in the quad that crosses the hip, and it makes up the bulk of the muscle located in the superior and middle compartments of the thigh. It lays over the vastus intermedius and parts of the vastus lateralis and vastus medialis. The rectus femoris is attached in two spots to the pelvis, on the anterior inferior iliac spine and on the supraacetabular groove of the ilium. The attachment points then converge into one tendon, which inserts into the patella and tibial tuberosity via the quadriceps femoris tendon. The rectus femoris has two main functions: to extend or flex the knee, and to assist in flexing the hip and thigh at the thigh joint. First, the rectus femoris acts alongside the primary hip flexor, called the iliopsoas, to flex the hip forward. Its anterior attachment to the pelvis allows it to pull the thigh forward to do this. Second, together with the other muscles in the quadricep, it flexes the knee. The rectus femoris is key in generating the force needed for lifting your leg off the ground. Further, it pulls up on the patellar tendon, which then pulls on the tibial tuberosity, which causes the knee to straighten. Next, let's look at how the rectus femoris specifically plays a role in mountain biking. But first, we need to understand a little bit more about cycling mechanics. Biking is thought of in terms of the quote-unquote pedal stroke. A pedal stroke means the complete rotation of the pedals, encompassing both the power phase, where you push down, and the recovery phase, where you pull up. Together, these phases propel the bike forward. A pedal stroke is divided into 4 quadrants of 90 degrees that together make up one complete revolution. It is often thought of as a clock face. The rectus femoris is most active during the first and fourth quadrants of the pedal stroke, when the knee extends and when you pull up to finish a revolution. Along with other muscles like the glutes, hamstrings, and other quad muscles, the rectus femoris works to generate the force needed to push the pedal down in the power stage of the first quadrant. Finally, the rectus femoris helps lift the leg during the upstroke and generally facilitates knee movement throughout the pedal stroke as described earlier in the anatomy section.
To show how the force of contraction of a muscle like the rectus femoris is translated to a force onto the pedals, I'll model the system as 2 bars and a hinge. So our 2 bars would be the bone that goes through your thigh, your knee joint, and your tibia bone, which is your calf. Here on this side would be the hips, and on this side is your ankle and your foot. So, in order to do this, we'll show that the rectus femoris comes along here. That's the muscle. And that it tapers down to a tendon, which is the patellar tendon, which attaches to the tibial tuberosity at a certain distance. Let's call that a distance of L away from the patella, or the knee joint. This also attaches at a certain angle, theta. That patellar tendon looks like this, and the tibia bone looks like this. So here is the tendon, the thicker one, and this is our angle theta. So, in order to transfer that force, we can see that the contraction, a certain force of contraction, will produce a force along the tendon, which will then, I'll call that Fm for muscle. So that force will produce a torque. So torque is the cross product of your radius and your force. And so the magnitude of such a torque would be Rf sine theta. So the magnitude of the torque from our muscle is going to be equal to R, the distance from the pivot point, which is L, so L, F, M, sine theta. Perfect. That is just the torque produced by the muscle. However, there will be an opposing force. So you can see that since this is the ankle, this is a little bit sideways, or very much sideways. But if the pedal were here, this is the surface of the pedal. You can imagine if this is rotated 90 degrees clockwise, it would be upright. But any force that is produced onto from the leg onto the pedal, that force will be the same as some sort of normal force here. So I'll have a normal force here, and that will be a certain angle away from the shin bone. So the normal force and the tibia make a certain angle. It's a different angle from this one, and I will call this angle phi. This here is phi. So the torque that this produces is going to be, the magnitude of that torque is going to be a different r. Let's call it d, the entire length of the tibia. That's going to be d. N is equal to the F onto the pedal, right? So I'm going to call that FP, dFP sine phi. Same process as the last one. And then now for the sum of all of our torques, that is going to be equal to, let's define that counterclockwise is the positive direction for rotation. So the torque produced by the muscle, the Fm torque, is going to be positive. L Fm sine theta. And the torque, the normal force torque, is going to be clockwise, and so that is a negative sign in front of that, different direction. So dFP sine phi. That's going to be equal to our total angular acceleration times the moment of inertia of that shin bone. So rearranging, we get LFM sine theta minus I alpha is equal to d FP sine phi, and then divide by d sine phi. So if I erase these and put them on the other end, divide by d sine phi. So this is our final equation that relates the force of contraction of your muscle to the force that your ankle produces onto your foot produces onto the pedal. Alpha and phi are going to vary depending on what part of the pedal stroke you are in, but L, theta, and D are all constants, as well as I. So this is the final model. The assumptions that are made here are that the muscles and tendons slide frictionlessly across any surface they're in, which is a bold assumption because your muscles and tendons are in constant, they will have friction along other things as they are inside of your skin and have direct contact with other tissues and muscles and other things. So that will contribute some sort of friction. Also, theta, L, and D will all slightly vary, but we are assuming that they are constants. They will slightly vary because the patella, within the movement of the knee, the extension, it does move around slightly. So these are the...
Next, we're going to provide a mathematical model that connects the work done by the rectus femoris and the rest of the quadricep group to the action done by the bicycle. A bike's pedal is connected to its front chainring so that as the pedal is pushed down, the chainring spins. Each cog has a certain number of teeth, and they're connected by a chain, so that when the chain rotates through one tooth at the front, it simultaneously rotates through one tooth at the rear. In this manner, if the front cog has, say, 10 teeth, and the rear has, say, 50 teeth, one rotation of the pedal, one pedal stroke, will bring the front chainring 360 degrees, but it will only move 10 teeth in the rear, which is a fifth of a rotation, and the rear cog will only rotate 72 degrees. The wheel is connected to the rear chainring, to the rear cog, so if the cog is only rotating 72 degrees, the rear wheel is also only moving a fifth of a rotation. In order to make this mathematical model, we have to assume a number of things. Firstly, it must be assumed that the weight of the rider and the bike are evenly distributed between the two wheels. So focusing solely on the rear wheel, we can look at 50% of the mass of the rider and bike system. Additionally, we will be assuming that the velocity is constant, and so acceleration is 0. We're going to start by drawing a hill, and this hill is an angle theta from the ground, and on this hill lies a wheel. This is going to be the rear wheel of the bicycle. and it's connected to the rest of the bike, but we're not going to worry about that. So we'll put our reference axes this way, with x positive being here and y positive being here. So the wheel has an mg that comes straight down, but because that's not aligned with our reference axes, we're going to be saying that there's a component that goes here, and this is mg cosine theta, and also a component that goes here, and this is mg sine theta. So normal force will go this way, normal force, and a force is being applied in this direction. So there's friction, and it's going to point this way because if it was the other direction, then the torques wouldn't add to 0, and because velocity is constant and acceleration is therefore 0, the torques have to sum to 0. Those are the down. V is constant. So next we're going to sum our forces real quick. So in the x direction, sum of all forces x, we have normal force minus mg cosine theta equals ma, but that's going to be 0. So therefore, normal force equals mg cosine theta. And then in the same way in the y direction, we can find that the force applied plus the force of friction equals mg sine theta. Now, we're not actually going to use this bottom equation because there's an easier way to do this. So because the sum of all torques equals 0, well, let's say that this is the rear cassette of the bicycle, and the rear cassette is going to have a radius of L, and then the radius of the wheel will be R. So because of that, we can say that the radius is R plus L times the force applied is going to equal R mg sine theta. If you look at this diagram of this bike, you'll notice that the front chainring is connected to the rear cog by the chain, and so therefore if you produce a torque on the pedal, which rotates the front chainring, that's going to be equal to the torque on the rear, on the cog, and less radius in the front, so more force, and so there's less force on the back because the radius is larger, and that expands to the wheel too, where the wheel is larger, so there's going to be less force but the same amount of torque. So this whole equation over here is going to be, each side of this is going to be torque 2, let's call it, which is going to be the torque in the cog. And we can say that the ratio N1 over N2, which is going to be the teeth, the number of teeth in the chainring, over the number of teeth in the cog, equals the torque in the chainring, let's call that torque 1, over the torque in the cog, which is torque 2, which is the torque that we have over here. Therefore, N1 over N2 times T2 equals T1. And we can plug in, we don't know what the force applied is, so we're not going to use this side, but we do know each of these things. And so we can say that N1 times T2, which is just R mg sine theta, divided by N2 equals T1. And then if we take that and we divide it by the radius of the crank, so let's put that over here, sorry, N1 R mg sine theta over N2, and then we divide that whole thing by the radius of the crank. I guess we've called that L up here. That gives us the force applied on the cog.